Okay, I think we should get started. Good evening, everybody. I am Sergio Volante, the chairman of the Space Astronomy Technical Committee, which has proposed this highlight lectures, and I will introduce the speaker for this conference. Pietro Ubertini, Professor Pietro Ubertini, is from the Institute of Space Astrophysics and Cosmic Physics in Rome, which is one of the laboratories of the Italian National Institute of Astrophysics. Pietro has been involved from the early 70s in Italy, but also across the world, I would say, certainly in Europe and in the US, in the design and development of novel X and gamma ray detectors for space experiments. Through this activity, he got involved in the development of the first generation of hard X-ray instrument, and of course, he got involved in space missions. I will mention the French-Russian Sigma gamma ray telescope flown at the end of the 80s. He was involved in the Beppo-Sachs Italian X-ray mission, which flew in the mid-90s, and ultimately he was the principal investigator on one of the instruments on Integral, an ESA mission, a gamma ray observatory which is still in operation. As co-investigator of the wide field camera on the Beppo-Sachs mission, he contributed to the resolution of a long-standing problem related to the origin of gamma ray bursts. The mission demonstrated that these gamma ray bursts were of extragalactic origin, and for this achievement, the Beppo-Sachs team received the Bruno Rossi Prize from the American Astronomical Society. His institute has provided major contribution also to Agile, a gamma ray mission from the Italian Space Agency, which was launched in 2007. And the Institute also has been involved in solar system missions. I would mention missions such as Rosetta and ESA missions to a comet, Huygens, which landed on Titan, Mars and Venus Express, two ESA missions which are still in operation, and also in NASA's Dawn mission. The most important achievement, of course, of Pietro Ubertini is responsibility for providing the IBIS imager, the workhorse instrument on the Integral ESA mission, which has led to many discoveries. He will probably mention in his lecture some of these discoveries. He's been instrumental in establishing the link between X and gamma ray astronomy and in contributing to the development of this discipline. As director of the Institute since 2005, he has boosted the R&D activity, in particular in the area of cutting-edge cryogenic detectors for space missions, but also for solar system missions. These efforts have allowed the Institute to be at the forefront in the proposal for instruments of new missions, such as Athena, Loft, Lobster, which are presently under study either at ESA or at NASA. Of course, Pietro Ubertini, through his activities, has been involved and still is in a large number of committees, working groups, etc. In particular, he was an active member of the Astronomy Working Group of ESA, a consultative group of ESA, and presently is heading a working group of COSPAR, the Committee on Space Research, which deals indeed with the future of space astronomy. So without further ado, I will now give the floor to Professor Pietro Ubertini. Thank you.
Thank you very much, Sergio, for your nice word. You're too good with me. And after this introduction, it won't be easy to maintain the level you depicted. So good afternoon, actually good evening, ladies and gentlemen, distinguished guests and delegates. First of all, I want to thank the IAF president for this invitation and Sergio for having organized this talk. I'll try to you in a short, hopefully interesting trip across the universe. That is not an easy task in 60 minutes, but don't worry, I will not spend more than 45, maybe less, so your dinner is not in danger, at least as far as myself concerned. The talk is organized in two parts. The first part is related to some achievement, the major achievement we have had in the last two decades in high-energy astrophysics and in general in the space astrophysics. And then I will show you that we are in deep crisis with missions, with satellites, and we may enter in a sort of dark age for the science from space. But let's start. Space satellites, as you know very well, has given astrophysicists a unique opportunity to explore the invisible part of the electromagnetic spectrum and drastically improve our knowledge of the universe. I mentioned the electromagnetic spectrum because there are other astrophysical branches coming, the gravitational waves, for example, then the non-electromagnetic part. And so I'm restricting my talk actually in the part that is connected with the light at any energy. The increased size, complexity, and cost of these large space observatories is placing surely a growing emphasis on large international collaboration, and this is the one theme that you will hear a few times during my talk: the need for international collaboration. We start a short virtual journey behind the known universe from its origin, and I put here two pictures. One is greatly representing the past scientific approach, the Romans and the Egyptian. This is a picture taken in Alexandria in Egypt. And you have your town, city here that is for me the future, what we expect in the future. So we start from the origin of the universe of black ball to the future, and finally realize that we are moving from a golden age, that is the actual age, and will continue for a while, from space astronomy to a possibly dark age. So just relax and let's start. The atmosphere is a very effective shield against radiation that may be very dangerous for us. Needless to say, the gamma ray, X-ray particles are producing cancer. The ultraviolet light may be very dangerous. When you go on the beach, you use your cream to shield yourself. So part of the radiation is blocked. In particular, thermal and far infrared are barely passing through the atmosphere. The UV sun light, the cosmic particle, and X and gamma ray. But at the same time, as I said, this prevent ground information, to get key ground information from ground on the sky and on the universe. So what we have to do is to go, you see, in gamma ray about 10 kilometers to see something, and the same in X-ray, even higher, 200-300 kilometers. We see part of the visible light, nothing in the ultraviolet, something in the infrared. And then you need airplane or higher media to go and to see the infrared part, and a very long wavelength radio is still visible from ground. So for this reason, space astronomy has started only very recently. Actually, the first breakthrough in the discovery of the celestial object was the discovery of a pulsar in SCO X1. This was done with a rocket by the group of Riccardo Giacconi, and for that he got Nobel Prize in 2002, actually 40 years after I did the measurements. what is interesting to see is that that rocket that's been used by Giacconi and his colleagues, and we used as well same rocket at the beginning of the 70s, were the original rocket planned to kill people, and then were reoriented after the Second World War, and that's why we had this blooming of instruments and space instrument and of results, because we could put that instruments out of the atmosphere. The rocket are our track to bring our instrument in the proper place in the atmosphere. But we have to start thinking that gamma rays and X-rays are not as the other radiation that we see, because a gamma ray can easily penetrate a 10 centimeter of lead or 1 meter of concrete. So you immediately understand that this energy band can give us information from remote part of the universe, because these photons can travel with no problem through interstellar matter and dust. So it's easier, it's possible to see really the more distant part of the universe with this detector working in this area. But let's see the universe multicolor aspect. Destroying the podium, sorry. This is a picture, sorry. This is a picture of the universe in different wavelengths, from radio to infrared to optical to soft X-ray, hard X-ray and gamma ray, increasing energy and longer wavelengths. This is an out-of-date picture now. 20 years ago, we thought that the universe was basically done in this way. Now we have a much better view. For example, we have new results from the new radio telescopes. This is a jodrell bank. You see that in the radio, we see very well the galactic ridge, and then there is something around the galactic disk. Very different in the higher energy, so more warmer part of the galaxy. We see very well the disk here, and then there is some information from the extragalactic part. This is our galaxy. This is the rest of the universe. In optical, we have, actually this is the near infrared. In the near infrared, we see very well the bulge, the galactic bulge, where the stars are formed, and the spiral arms where again the stars are formed, but there is not very much around. And then in the soft X-ray, the picture is completely different. In soft X-rays, we have 200,000 or 300,000 stars that are hot objects, basically distributed all in the galaxy and in the extragalactic. So you don't see this large amount of stars or high energy emitters in the plane. In the hard X-ray, the picture was very shaky, and then sorry, this is another, and then this is the new data, same set of data from ROSAT, but reanalyzed in a better way, and you see that there are now some sources coming out on the plane. In the hard X-ray and soft gamma ray, the picture was very shaky 20 years ago. We had only a handful of sources, 20 or 30, and there was the idea that the center of the galaxy was emitting a diffuse emission that was impossible to be explained. So one of the main tasks of integral and other gamma ray detector, gamma ray spacecraft, was to understand this mystery and give us a better picture, because these sources were positioned with half a degree or so. Now we have a much sharper view. I'm sorry, the picture is not very nice, but we have a much sharper view of the galaxy disk with more than 1,000 sources. We know that the center of the galaxy is permeated by, not by diffuse emission, but what we saw as a diffuse emission was a sort of blur image that was due to more than 100 sources, discrete sources, that now are fully resolved and fully understand. In the even high energy, the highest energy that we can see from the universe is operative since a few years. GLAST, now named Fermi, is a NASA gamma ray observatory that give us the information on the largest energy. And you see that are visible, that are detectable from the sky. And you see how much is the improvement from the EGRET, the gamma ray observatory that produced that data 20 years ago, to the Fermi that has a much sharper image. And again, at high energy, it may be strange, but the actual view is much more similar to what we see in the microwave and in other band, in the near infrared. Actually, there is a close connection between what we see from the galaxy in gamma ray and in infrared. And then we see a major amount of gamma ray sources all around the universe. And these are the largest beasts in the universe. In fact, one of the major results that came out of combined observation from Integral, ESA, and SWIFT, NASA, and the Fermi Gamma Ray Observatory was the discovery of very large amount of mass concentrated, talking about 10 billions, so 5 to 10 billions of solar masses concentrated in gigantic black holes that are at the border of what we can see now from the universe with our present instrumentation. I will see that later on. We will go back to that later on. So the present picture is quite good. We have a number of satellites that are looking at the sky from the space, complemented in the radio wavelength when we can observe with large dish from ground. So no competition between ground observatory of that kind with spacecraft, and at very high energy where the photons are not visible with the gamma ray spacecraft because we need hundreds of meters of type instrument. So the whole electromagnetic spectrum from the longer wavelength in the radio to the optical to the high energy is fully covered. And astronomers are very powerful tools to investigate any object they want to see at the limit of the sensitivity of their instruments. We have, I'll shortly mention the major observatories that are in place now that are flying. Planck Inertial launched a couple of years ago by the ESA Space Agency, great success in the infrared. Then we have WISE, Spitzer from NASA. We have the Hubble telescope that is a milestone for optical astronomy from space. We have Galaxy, Ultraviolet, SWIFT, and Integral, as I mentioned, that are working in parallel on gamma ray, in the gamma ray area. And the two major X-ray observatories that are Chandra and XMM that are giving us a terrific tool to study the distant object and the more hot part of the universe. And then finally Fermi and Agile. Fermi is a large space observatory from NASA, and Agile is a small satellite, as Sergio mentioned, is a very small satellite. To give you an idea, the cost is of the order of 60 million euro, but is in space since 3 years and is very successful. So we have spectacular results from this space observatory, but before going on, I want to give you a taste of the dimensions we are talking about. So we need to assess the right dimensions of our life place. From the apartment to the city. We live in an apartment that is the Earth, is our house, and our city, in a way, is the solar system. But how long we take to go from our apartment to the border of this city, that in other terms means how long do we need to explore the solar system? Can we go behind the solar system? The answer clearly is not. Not today, not unless we discover we can speed at the speed of light in the near future. People working on neutrino is trying to demonstrate that we can go faster than light, but we are talking about millions of orders of magnitude to increase this capability of the human being. Now we cannot go beyond exploration of the solar system because you know that the Pioneer probes that were launched in the 70s in 40 years are basically arrived at the border of the solar system with incredible results. But really, 40 years is the longest time we can imagine to send a probe and to have back results. So we can do a lot of in situ exploration. I think it's really the exploratory science that we should exploit as much as we can. But this is our city. But if we want to go far away, how much we have to go? This is the sun. And in the galaxy, that is our neighborhood, there are 100 billions of stars like the sun. Stars like the sun that last 3-4 billions of years as the sun. Others are much more, they die much more younger, million of years. The bigger the star, the less they last. But there are 100 billion objects to study here in our galaxy. And then this is a sort of our galaxy. It's not, of course, but it's similar to our one. It's the spiral galaxy seen with a telescope, of course. And how many there are? In the universe, we have 100 billions of galaxies. So we have 100 billions by 100 billions solar systems or star systems. And clearly, we hope to have at least one with some with similar environment as in the Earth. So looking for this exoplanet is surely a worth exercise as far as I see, because this will give us a handle of how much the life we know on the Earth has been replicated somewhere. But don't forget 100 billion of 100 billion. And at the larger scale, we don't have anything else. This is the universe. So universe is self-contained as far as we know. I mean, we are not philosophers, we are scientists. So for us, the universe ends at 10 to the 28 centimeter, more or less, and this is what we can study. So I promised you a tour in the black hole, but where are these black holes? There was a long quest. Black holes were hypothesized long ago by theoreticians. Then there was a long quest from black holes that were not found easily. And I will show you how this quest was difficult and how we solved the issue now. This is the radio image of our galaxy. Our galaxy is a sort of flat dish with a lot of mass in the center. 90% of the mass of our galaxy is here. You have seen the picture before. So really, if we have to look for a black hole, we have to look in the center. A radio telescope from ground and immediately seen strange activity, non-thermal, as we call, high activity from the radio source in the center of the galaxy called Sagittarius A, and the natural place to look for a black hole was this one. But of course, if you look at in the radio, you don't see anything particular. You see a blob of light. So no evidence in the radio. Now we know that there is a black hole of about 3.7 million solar masses in the center of our galaxy. It's a baby black hole. We're talking about millions of solar masses, not billions, as in the large structure on the universe. But where is this black hole? Why we don't see it? It should have a terrific power. So we know that, and you will see in a moment why. There is nothing particularly bright in the infrared picture. This is, again, the center of the galaxy. This is a hot material emitting, but we don't see anything spectacular. In the optical, of course, from the south, you can see the Milky Way, and you see a big block of dark due to the molecular clouds and dust. So there is nothing particular visible, actually nothing visible in the optical. But a group of scientists in Germany, led by Rainer Genzel, have made a very accurate work for 10 years. They've been looking in the infrared, because in the optical we don't see very much. They've been looking in the infrared at the stars orbiting the galactic center, and they have discovered that these stars, when they approach the galaxy center, they accelerate dramatically. You see here. They go very slow when they are far away, because they are attracted by the central object, and they become crazy when they are close. Looking at the dynamic of all these objects is really something very intriguing. They discover that there should be the matter equivalent to 3.6, 3.7 millions of solar equivalent there. So there is a black hole here. It's not yet. This is not yet the answer, because having 3-4 millions of stars in the center, in a big center, it doesn't mean that you have a black hole. You only know that there is this mass placed there. So we need another independent confirmation to see that this black hole is really there, and why we don't see it so bright. To do that, we have to go for X and gamma ray science, and this is a representation, is a simulation, but it's a realistic simulation of what we see looking at the neighbor of a black hole. This is considered to be the black hole in the center of the galaxy. Of course, you see nothing is black because light cannot come out from the center of the black hole, but the matter around is paralyzing, and is eventually swallowed by the black hole. And any star that would go closer to this black hole would be swallowed, would have been swallowed in the past. So really looking at this simulation, we understand two easy points that are known since ever. The black holes are only two ways to interact with the external environment. They spin, so they rotate, and then they rotate with the matter around them, and they have a gravitational effect. So the only two ways to look at black hole is to look for the rotation induced in the matter falling on the black hole and to the gravitational effect. Now, this is our galaxy, but we have to move far away. We have to move from this large black hole in our galaxy, because it's substantial, millions of solar masses, to the evolution of the universe. Looking at the evolution of the universe is easy in one hand and difficult on the other one. This is the representation of what is what we think about the universe evolution. We have the Big Bang here. Sometimes in the past there was a big explosion, and the matter and energy and the lights was melted together. I will show you in a moment how this is considered to happen. And then all this matter expanded very violently, and at the end, after this initial expansion, the major component of the universe was hydrogen. We call neutral hydrogen. So the elemental element that was the basic brick of the universe. But how this enormous amount of hydrogen has become, with time, after half a billion years, 1 billion years, how could become stars and planets and humankind. This is something that we have to study and to address. To do that, we have to see. I mean, the Chinese could see from the actual time only with naked eye very little. Though they discover supernova, they discover stars. And then with the telescope, with Galileo telescope, we made a big jump far away. And then since then, we have improved our digging in the universe. We try to dig back and back in the universe. And of course, because of the light needs 13.7 billion years to go from here to there, the more we look back, the more we look far, the more we see phenomena that happened long ago. So if we see a star exploding here, this has exploded 1 billion years after the Big Bang, and we will see not the star as it is now, but the travel time of the lights has permitted to this object to evolve, but we see it as it was at the beginning of the travel we are looking at. So if we look back, we learn more. But how much we have been back? The first cluster of galaxies, the one that you have seen before, an object with billions of stars and hundreds of thousands of galaxies, has been discovered, actually has been seen 1 billion of years ago. We say, actually it was 4 giga-year, 4 billion years ago, not ago, sorry, from the explosion of the Big Bang. And at Z 1.9, this is the number astronomers use very much, the redshift, because it gives you a physical measurements of you know exactly, if you see the redshift of an object, how far it is. So we know that this cluster is exactly in that position. This was seen with the Hubble telescope. Then the fastest ever object observed by astronomer is a gamma ray burst observed at the Swift Observatory and then studied in details for years, that has started 0.6 giga-year, so 600 million years after the Big Bang. I remind you that we are at almost 14 giga here, so really is very soon after the Big Bang in this picture. And we think these gamma ray bursts that are a batch of photons that arrive every day basically on the Earth, and these are due to explosion of star supernova, or eventually neutron star coalescent. In this case, because it's a short burst and very far away in elliptical galaxy, we think is due to neutron star to two neutron star spiralizing, okay. And why they coalesce, why they go one on the other one. That's because we think they lose, while these two neutron stars are rotating one close to the other one, they lose energy in the form of gravitational waves. So they lose energy and they spiralize more and more close, and then when they touch, they explode. And this blast was so big and so strong that could have been seen from very far away. But now the astronomer wish to see the first star, because we see a lot of stars, a lot of gamma ray bursts that are supernova explosion, but we want to see the first star, because this is one of the basic questions. How we moved from hydrogen, you remember that at the beginning we were only hydrogen, the universe was full of atoms, and then how from the atoms we arrived to the structure, to the galaxy, cluster of galaxy, and then single stars. And the astronomers have an idea now. This is a simulation starting from redshift 14, so really just after the Big Bang, when it was all hydrogen. And then the gravitational instability have given to this hydrogen the possibility to clumps in the small filaments and in small nodes. And this is a real simulation. It's not a picture. It's getting billions of particles of atoms of hydrogen and simulating their evolution. So we know now that we live in a cosmic web that has been generated because of this gravitational instability. And now you see when zeta is equal to 0 is today. So this picture is a good representation of the today situation for the hydrogen. And this material, when clustered together, is forming in some way in each node, in each density enhancement here or there, a gigantic black hole. One of the things that has been now accepted worldwide is that this gigantic black hole in extragalactic object in quasar are a sort of a seed on which the galaxies are growing up. So the black holes are the seed that have generated the galaxy, the first stars, and then even the planets. So few seconds to this is the same picture, different. So we want to go as far as we can close to the Big Bang, but the nuclear physicists have imagined what would have happened at the very beginning. So they were able to invent a model to go from 10 to the minus 43 seconds to 10 to the minus 35 with some scientific background, I mean, a strong scientific reason, and then they can understand what happened 10 picoseconds, 10 to the minus 12 seconds after the Big Bang, up to minutes, to thousands of years, 100,000 years. Clearly, we think we understand what happened from the beginning to basically 100,000 years. And then there is a time in which that is the dark age for the universe, because the hydrogen was not neutral, was in a way ionized, so it is impossible to see through this matter. So we will never have a chance to see what happens here, but surely we want to go as close as possible to this dark period. This is another simulation. Is called the Millennium because there are 10 billions of particles simulated. Each particle is one galaxy, and you see now how this web structure, that is the whole universe, now we zoom in a smaller and smaller scale, and you see this sort of neuronic web, spider web, that is the universe. These are large structures, superclusters, and then when we go inside, we will see that there are a smaller structure, the clusters, and that smaller structure, the galaxies, and so on till to arrive to stars and eventually planetary systems. So this is a good simulation, but it may be completely crap. Is that true? How can we check that this invention, that this is, even if it's done with the best computer we have, with the best information we have? Of course, astronomers are not completely stupid, and they cross-checked these results with the observations. And the observations are this one. Let me check. Okay. Okay. These now are real data. Each point is a galaxy measured again from ground with patient work. The red points are the one in which there are several galaxies measured, and of course this is a small part of the universe. This is too light. I think the diameter is only. Let me see. I think it's 2 billion light years, so it's 2 billion lights here, and there are 100 billion galaxies. And what you see here, what you see here is that the structure that we measure from ground is exactly as the one that has been simulated and demonstrated to be possible from the original hydrogen distribution. Yeah, the circle here is 2 billion light here. So the lights need 2 billion here to come from here to there. So this is quite far away. This is the border of the known-universe that we see today. But we have to take into account a drastic fact. We know we are very ignorant. All we see in terms of matter is only 4% of the matter that is necessary to explain what we see from the sky. And this is a problem because we know that 96% of what should be there to explain all I've shown you before is in the form of dark matter, 23% cold dark matter, and 73% dark energy. Without that energy and without that matter, the universe will not stay together. We cannot explain it all. Then there are two hypotheses. One is that we have to find this dark matter and dark energy, so we know that we don't know because we don't see it, or there is something fundamental wrong in all the hypotheses we have done on the universe evolution, and we think this is not the case. So we have to look for this dark matter. This is a picture I took yesterday from Nanzang, and it is nice because the dark matter and dark energy, he said, are considered the two dark clouds hovering above modern physics, and also the key to understanding the origin and evolution of the universe. A few days ago, ESA has approved a mission called Euclid that is exactly due to discover the dark matter. So hopefully in a few years we will have answer to that question. And while I was talking, I was expected to show you how astronomers have simulated with computers, with powerful computers, the evolution of the dark matter. Of course, we need a dark matter more or less where the visible matter is to keep the universe together. But this is again another demonstration that we can mimic what we expect to be there even if we don't see it. Okay. Now we go to. We know that from the gas, we have the gigantic structure, so-called quasar. This is a simulation of quasar interacting in the far and distant universe from Z very high, so from the beginning of the formation to date. And you see that this big structure formed by galaxies and supergalaxies are interacting together. And this is a way to combine big black holes in supermassive black hole in gigantic black hole. The effect is that matter is ejected, pieces of galaxies are ejected, and we know that this is the way, now we think this is the way the universe has formed from the gas to the gigantic structure and then to the galaxy. But how are these galaxies interacting together? This is another simulation on a very smaller scale. Now we see two galaxies similar to the Earth, our galaxy. This is a spiral. These two spiral galaxies interact each other and exchange matter, dark matter, energy, stars, and the nuclei of the two galaxies may grow up. The galaxy that is winning is getting out matter from the other one. There are big tails of matter exploded in the space. And at the end, these two galaxies will become a twin. Eventually, they will collapse one on the other one, because the time scale here is a giga-year. It's not anymore 10 giga-year, but 1 giga-year. So this is a smaller scale evolution, and this may be our galaxy. You see here in the simulation, there is a neutron star pulsating in the center of one of the two galaxies. Now, is this again true, or is just invention? Of course, it is true. You see a beautiful picture from Hubble telescope. These are two interacting spiral galaxies called NGC 2207 and IC 2163, and you see that they are exactly interacting. Of course, astronomers looking at the stars, looking at the matter around, can make a solid hypothesis of what they see, and this is a way to cross-check what they have simulated very successfully. I showed you before. So we have galaxy with black hole, quasar and distant object with even more big black hole, and galaxy with small black hole like our galaxy. Another spectacular image is what we get. This is the best we can do ever with the telescope, with the Hubble Space Telescope in an ultra-deep field. There are lensing galaxies due to the gravitational effect explained very well by Einstein. There are a spiral galaxy like our one. There are elliptic galaxies, single stars that are in the field. And you see a cluster of galaxies. So this is actually one of the deepest fields we can get with this telescope with a long observation. And this was, I remind you that this year, Hubble has spent almost 21 years, more than 21 years in orbit. But if we want to see really the black hole, we haven't seen it yet, because we have indication that there is a black hole, but where is the black hole? To see black hole, we have to go to X and gamma rays, in particular to gamma rays. This is a picture, enlarged picture, what I've showed you before, is an integral picture of the galaxy plane. This is the amount, the number of objects that are in the galaxy. Is an exposure. We spend almost 30 megaseconds to see that image. 30 megaseconds mean more than 1 year. So the satellite has now 9 years, is in orbit since 9 years. And to get this image, we have spent more than 1.5 years. So you imagine that to have a better image, we need a terrifically better instrument, or an instrument that can last for 100 years or so. So really, we need a forward step if we want to do better than that. But looking with integral that have a very good angular resolution, can pinpoint sources to a level of few tenths of arc seconds, we see the galactic center. This is a Sagittarius A I showed you before, and this is the object in the galactic center, is the black hole. It's not very active. In fact, there is another guy here that is much more active than him. This is a small black hole, and is very effective. The reason is very simple. This is a gigantic black hole, so the matter cannot go very close by to the black hole, so it's not very active, it's not very strongly emitting, while a smaller black hole even has less energy, but can clearly attract matter more close by, and so the matter becomes more hot, and we see a more active activity to this object. So this is a young and excited, this is old and quiet. As I said to you, gamma ray can penetrate 10 centimeters of lead, and deep integral and swift observation have revealed the existence of obscure black hole. The black hole I've shown you before in optical, the galaxy I've shown you before in optical and in simulation have been observed by integral and by swift, and we know now that roughly 25% of this gigantic object at the border of the universe are made out of a big black hole. Inside there is a torus around of dust. You see, this is of course a pictorial image, it's not a real image. But we know that now these objects are made out of a big amount of gas and dust around the black hole, and the black hole eventually emits jets in our direction. When we see these jets, we detect this object, and we can measure the mass of this object. And we know, doing a proper computation, that this object have now 5 billion solar masses or more. And this is the first tomography we did with integral and swift, because looking at this object, we don't see the object itself. We see the X-ray and gamma ray coming out of the object. So it's very similar to the picture you get when you have a problem, you break your arm and you go to hospital and you get the tomography. This is a real TAC. But the important point is that we have not seen before this object because they were completely obscured. And in gamma ray, we understand the mass. They are very big, actually. And then this is a picture of the very highest energy, gamma ray. Basically, the universe is populated by pulsar in the galaxy plane, as you see here, and by this gigantic extragalactic object here and there. So this is one of the sharpest images obtained with Fermi, and this is the best we can do to date. Chandra, for example, and XMM are studying single object. This is a supernova remnant observed by Chandra. It's a beautiful, sharp image. You see the ejecta of the supernova that was in the center. You see this point. When exploded, a number of elements were ejected, and according with the color, we have different elements. So we can actually measure the amount of carbon, of sulfur, of nickel we have ejected from the supernova. And we also have detailed information about the magnetic field and the blast wave that at the edge of the supernova is interacting with the interstellar medium here. So we have really quantitative information on the supernova, etc. I will conclude this first part in half an hour, and then another 10 minutes, so don't worry too much. Showing you 3 pictures of Andromeda. This is a very old picture. I remember when I started my thesis in the 70s, there was a picture like that in my institute. I thought, what is that? I mean, it was very, very attractive for me, very sexy, if I can say. Is a galaxy that is close by, and these are the stars. Now we have incredibly different picture. This is a picture taken not long ago by Herschel. Is one of these cryogenic mission. Is one of the cornerstone of ESA. It took more than 20 years from the ideation to have this in space. But you see immediately the trace. These fleshy parts are the part where there is a stellar formation. So the part more hot are the one that in the galaxy are where the galaxy is forming the baby stars. So this part are these parts that are fleshy, that connected with the spiral arms, are the part of the galaxy that are more active in forming stars. You see there is this arch here, not very much in the center. Conversely, in the optical, you see all this batch of stars that have been already generated. So this is the present life of stars. This is the stars when they are born. And then if you look at the image with XMM Newton, the X-ray telescope from ESA, you see that there are a terrific number of stars that are dead. These are black holes and neutron stars that emit very high energy. So these are the highest energy. So in a way, we go from the living stars that are this one, known since ever, to the birth of stars that are the red part, and you see that they coincide basically with the spiral arm, but not with the center, because the stars in the center have been already built and dead. And where are the dead stars? The dead stars in the center are here. They are spot clearly with XMM, because they are neutron stars and black holes, so they emit a large amount of energy. So with these 3 pictures, you see the fate of the galaxy, from the very beginning, the red, to the normal life, the white, to the high energy emission when they are dead, black hole and neutron star, basically. So really is a powerful tool that we have. But now, now this is the state of art, but which are the open questions? Let me go through quickly. We need to probe the very early stages of the universe to understand how it evolved from the Big Bang that you have seen, from the pure hydrogen in form of gas to the monster and the mini black holes. The ones that are in the galaxy. How and when the first star will build? This is a question that does not be answered, because the first stars are the more far away, the more difficult to reach, to observe, and we may eventually need a new generation of space observatory to give an answer to that. These are among the more fundamental questions. We need for more and powerful observatories, as I said. And there is also a need to maintain a full access to the whole electromagnetic spectrum. If you remember the picture I showed you before, now we have a full coverage from radio to very high energy, ground and space. What we cannot do from ground, we do from space. This is a perfect marriage between ground and space. And it worked very well in the last 20 years. So there is a solid plan for ground-based facilities, and this must be complemented by the space segment to get the full picture of the universe originated and what it's made of. We have an unsecured future for large mission. This is the basic message I will give you in the last 5 minutes, and the reason is very simple. Starting from this worry for the future, Roger Boneda was the former president, actually was scientific director of ESA at the time of Sergio, and then became a former president of COSPA. Last year in Bremen, he set up a working group that I have the honor to chair. And this working group was then confirmed by Nanni Bignami, that is the actual president, to look at the situation and to understand with the scientific eyes. We are a number of people just put together. We are scientists from all over the world, and we are trying to understand which are the problems and how can be attacked. So this working group has been working for 1 year now. It has been set up in April 2010. In March, in springtime this year, we have made a report. We have presented in several places our results, and I'm honored to be here to present again to this different audience what are our reflections. And we have identified some major concern about the lack of a future of space astronomy, and this is the result. Of course, I will be very pleased on behalf of my colleagues to receive back suggestion, criticism, throw tomatoes if you want, but I think this is what we see. And the report is going to be published as an ASR paper soon, an 85-page report, and will be presented at the next COSPA meeting in Mysore, India, in July next year, and at the IAU meeting in Beijing, China. This is the working group. It's really international, but the basic consideration are astronomers need access to the complete electromagnetic spectrum, which requires ambitious and powerful observatories as multinational ground-based project, as well as large space mission based on international cooperation and coordination. International cooperation will not be implemented. If it will not be implemented, new missions may not be as powerful as they could, and may result in unnecessary duplication or not occur at all. This is a very shaky point. The working group believes that the scientific community at large, so you and your friends, should find ways to provide the necessary encouragement and support. Of course, for the agency it's not easy to join together to do the extra work necessary, but we have to help them to create the condition in which international cooperation can bring about a better scientific outcome and goal. Today, operational space observatory cover the whole electromagnetic spectrum and complement ground-based. There are a number of satellites I will not repeat because it's late, but some of them are in operation since more than 10 years and are becoming old. They may die one moment or the other one. And of course, this is not something that we like, but the delay of James Webb and the cost is, in a way, a major concern for the working group. So we now have all these satellites operative. In 5 years' time, some of them will be dead. Surely, James Webb will not be in place. We will have a few more like Gaia, GEMS, small satellites, though good science, but not very big. Herschel and Planck will have finished their cryogenic life. And so we may be in a situation after 2018, 2020, where we have really nothing. If Athena is not selected, if Spica is not selected, and I understand Spica is not in very good condition, money-wise from Japan's side, we may have only James Webb and other small or medium-sized satellites, so the situation may become really bad. In green, you see the situation now. These are all operative satellites. The green one from the Hubble telescope 20 years to the recently launched Herschel and Planck, WISE, MAXI, AstroSat will come, and these are the ones to come. So we had from the 2000 a great amount of observatories. We may result with zero. This is not a fake picture. In 2020, 2025, there are basically known observatories approved. So a community of thousands of scientists may really starve. To be short, our initiative have been brought around the world. As you know, I presented in May 2011 some reflections, and Malcolm Longer, a distinguished astronomer, have presented a sort of review for the decadal survey, and then there was another reaction recently, a paper by Bonnet and Blicher, addressing the possibility to have this dark age for space astronomy. The Malcolm Longer results is very similar to what we have. International collaboration is essential. Maintaining a long-term vision requires persistence and patience. Technological advance is important. We have to maintain an effective program of medium and small mission on top of the larger observatories, public engagement, and so on. So only a few of the top priority large projects are eventually approved, and this is something that is valid for the last 20, 30 years, so will be valid for the next 20 or 30 years. Many projects disappear. Many of the largest programs are international. The projects are generally at the limits of the technological capability, otherwise they are not interesting, really, and at the bleeding edge of technology. The projects are generally take longer than planned. Some are in the list for several decades. So what we are discussing now is really valid for the next 20 or 30 years. And the costing of the programs are generally underestimated. This is a bad point for us and for the space agencies. And which are the conclusions? We really go to the last two view graphs. Some of the working group report conclusions have been reaffirmed in a paper by Bondet and Blicher. Of particular interest for us, for the working group, are the conclusions about the lack of a common planning and management controlled by space agency in the last decade. You have seen ESA and NASA and JAXA have studied IXO, the X-ray observatory, LISA, the gravitational observatory, and the planetary mission to JSM for 15 years, and now they have decided to go each other, to go alone, to divorce. So we start again after 15 years. At the time of a worldwide restricted financial capabilities, the lack of common strategy at the international level is becoming a major stumbling block. Each national roadmap has its own planning of mission that may introduce useless duplication and or prevent collaboration on required global observatories. And as I said, this is exemplified by the ESA NASA JAXA roadmap for the mission IXO, LISA, and JSM, which result in a downscaling of the major observatories for the worldwide community. Second conclusion is that strategic long-term planning, at least 2 decades, is essential in order to establish a single roadmap, single worldwide roadmap based on global cooperation, which clearly identifies scientific priorities with the required technological development that is not easy to achieve. This can be implemented maybe through an interagency coordination group. This is the conclusion of the paper from Roger Bonnet and Johann Blicher on a large space astronomy facility. Examples of such an approach exist. The agencies have already done this successfully for other efforts. For example, the Committee on Earth Observation Satellites, the International Space Exploration Coordination Group, and the International Committee on Global Navigational Satellite System, without the necessity for intergovernmental agreement on budget. So we're not talking about budget here. And if all the above happens, we will have a revolutionized view of the universe in the next 2 decades time frame, as we had in the last 2 decades. Thank you very much for your attention.
Thank you, Pietro. Well, the paper is open for quick questions in the audience. Yes?
Apart from India, I'm less interested in the policy issue, more interested in science. And have any projects or any experiments that can give light on dark energy research? Because most of our work has been in the labs and the colliders, but there also we do not have any research.
Yeah, I had no time to go in details, but actually the Euclid project from ESA side that is more oriented on dark energy is also, we also give a handle on dark matter, and the WFIRST project that is the top priority for the decadal server just studied from NASA is more tuned for the dark energy. So we recommended as a working group that these two projects should be jointly exploited. In this way, we will have a better science packet. We will be able to see the dark energy up to a certain fraction and the dark matter at the same time. Having the two projects together may hamper this possibility, but surely it's very clear for the agencies and for the scientists that this is an opportunity that we are barely going to miss, because now ESA has decided, maybe rightly, to go on without NASA. And it's shocking that NASA has WFIRST as the first priority, so we would expect that the two agencies talk each other and go on a single experiment. There are other problems related, for example, with the detectors, with the technologies, that could be easily solved putting the two spacecraft together, the two ideas together.
Other question? Yes, Jeff?
I'd like to make the point that in addition to international cooperation, we also need to be coordinating the future exploration program with the scientific program. Why has Hubble been with us for 21 years? It's because we've been servicing it 5 times. And it doesn't necessarily have to be human servicing. It can also be robotic servicing. But we talk about developing these deep space capabilities. The science community should be able to take advantage of it, because we can't afford to keep building these new huge observatories every 10 years. If you can build one, like we do telescopes on the ground, and service it, we have a lot more for our money. And I think that's the way to go in the future.
Yeah, I fully agree. I didn't have time to show you, but maybe I have a picture to show you quickly. These are is only for the high energy experiments, and at the beginning were the whole lot. But if you see from the 60 to now to the 80, there were a lot of satellites shortly lasting. Then between 80 and 90, the trend changed completely. Now we have a long-lasting great observatory. So the servicing, as you said, and the cost to maintain that in space is really a burden. And I completely agree with you that we should find a way to minimize the cost and to have at least one great observatory every decade. I would sign it immediately. We will not have one for at least 15 years, I'm afraid. Of course, things may change, and what have been done at the level of the working group is now apparently well received. The fact that this audience is not empty is a good sign for me, for my colleagues. But we surely may try to convince our space agency to have a more effective policy, in particular talking each other. But I completely share your point.
More comments or questions? If not, thank you again to the speaker. And have a good evening and a good dinner.
Thank you for being here.